What if I told you that the second most famous spacecraft in human history just quietly did something the first one physically could not do, and almost nobody noticed? Right now, 13 billion miles from your window, a machine older than most people watching this video is carrying an instrument that has already rewritten what we thought we knew about the edge of our solar system. Before I go further, do me one small favor. If you love space, if you love the kind of story that takes you somewhere no telescope can ever reach, hit that like button, subscribe, and share this video with one person who still looks up at the sky and wonders. That one click keeps stories like this alive. Now let me take you out there. Most people, when they hear the word Voyager, think of one spacecraft. They think of the golden record, the pale blue dot, the endless headlines about the farthest human-made object ever built. They think of Voyager 1, and Voyager 1 deserves that fame. It really does. But there is a second machine out there, quieter, less famous, traveling in a completely different direction through a completely different slice of interstellar space. And that quieter machine is carrying something Voyager 1 lost before it ever came close to the edge. Something small, something almost forgotten. Something that turned out to be the single most important tool humans have ever used to understand what actually happens where our sun's influence finally ends. That machine is Voyager 2. And what it measured when it crossed into interstellar space did not just add to what Voyager 1 discovered. It challenged it, it complicated it. In some places, it flat out contradicted it. Because Voyager 1 was, in a very specific and very painful way, blind. And Voyager 2 was not. To understand why this matters, we have to go back to the summer of 1977, a time before personal computers, before the internet, before cell phones, before most of the engineers alive today were even born. 2 spacecraft were being prepared for launch. They looked almost identical. Same body, same antenna, same instruments, same plutonium generators quietly ticking down inside them. But their missions were not identical, not even close. Voyager 2 launched first on August 20th, 1977. Voyager 1 followed 16 days later. The naming looks backwards, but it is not a mistake. Voyager 1 was placed on a faster track, aimed straight at Jupiter and Saturn and then out into deep space. Voyager 2 was given a slower, longer, stranger road. A road that would let it do something no spacecraft had ever done before, something no spacecraft has ever done since. Voyager 2 became the only machine in the history of humanity to visit all 4 giant planets: Jupiter, Saturn, Uranus, Neptune. Every single gas and ice giant in our solar system, up close, in detail, with cameras clicking and instruments listening. Voyager 1 skipped that. It cut its trip short after Saturn. It swung by Saturn's moon Titan and then turned upward, out of the flat plane where the planets live. It sacrificed Uranus and Neptune in exchange for a faster path to the stars. 2 spacecraft, 2 decisions, 2 very different answers to the same question. What does the outer edge of our solar system actually look like? Voyager 1 chose speed. Voyager 2 chose completeness. And that choice, made when disco was still playing on the radio, would end up shaping one of the most important scientific discoveries of the 21st century in a way no one could have predicted. Because time did something strange to these 2 machines. Voyager 1 raced ahead. It crossed into interstellar space in August of 2012. Voyager 2 didn't cross that same invisible line until November 5th, 2018, 6 years and 3 months later. And in those 6 years, something quietly went wrong with the story. Voyager 1 was sending back data that scientists were struggling to explain. The models were breaking, the predictions were off, the edge of the solar system was not behaving the way anyone had drawn it on a chalkboard. But Voyager 1 could only tell part of the story. Because Voyager 1 was carrying a ghost. Here's the part almost no one ever mentions when they talk about Voyager 1. In 1980, before Voyager 1 had even reached Jupiter, one of its most important instruments simply stopped working. It was called the plasma science instrument. Its job was to directly measure the invisible sea of charged particles the sun blows out into space, the same sea that eventually thins out and meets the plasma that fills the space between stars. That instrument was the eyes and ears of the mission for anything to do with the wind of the sun and the boundary where it ends. And it died. Not near the edge of the solar system, not in some dramatic radiation storm. It died early, quietly, decades before it would have been needed the most. So when Voyager 1 finally crossed into interstellar space in 2012, it did so without the ability to directly measure the very thing that defined the crossing. Scientists had to piece the story together from other instruments: the cosmic ray detector, the magnetometer, the plasma wave subsystem, all good tools, but none of them could do what that one broken instrument was designed to do. For 32 years, there had been a hole in the data, and no matter how brilliant the scientists on Earth were, they could not fill it. And then, 6 years later, Voyager 2 arrived at the edge, and Voyager 2's plasma science instrument was still alive, still working, still humming quietly across billions of miles of dark, cold space. On November 5th, 2018, that instrument became the first human-made device in history to directly measure the plasma on both sides of the boundary. Take a breath and let that sink in. For the very first time, a machine built by human hands stood on the doorstep of interstellar space. It looked at the wind of our own sun on one side and the wind of the galaxy on the other and measured both of them in real time as it walked through the door. If your mind isn't quietly blown right now, wait. Because what it saw did not match what anyone had drawn. In November 2019, something rare happened in science. 5 separate research papers were published on the same day in the same journal, Nature Astronomy. 5 papers at once. That does not happen unless something enormous has been discovered. And what those papers described shook the field. The first shock was about the shape of the boundary itself. Scientists had always pictured the edge of our solar system as a wall, a thin, sharp line, maybe a few 100,000 kilometers wide, where the wind from our sun ended and the plasma of the galaxy began. 2 rooms, 1 door. Clean. Simple. Voyager 2 said no. What Voyager 2 found was not a wall. It was a shoreline, a messy, layered zone about 100 million miles wide, sitting just outside the boundary. Not clean, not sharp. Interstellar particles were reaching inward, pushing into our solar system's outer skin like roots creeping through cracks in a rock. And that mixing zone existed in a place where, according to every model, there should have been nothing but pure interstellar space. And there was more. When Voyager 1 had approached that same boundary years earlier, it had seen something strange too. It had entered a place where the solar wind had almost stopped. A dead zone, where the sun's breath was running out of power and slowing to a crawl. When Voyager 2 approached the same edge from a completely different direction, it did not see the same dead zone. It saw a thin transition layer of roughly the same thickness, but with entirely different plasma inside it. Different personality, different behavior, same boundary, 2 crossings, 2 spacecraft, 6 years apart. And the boundary looked like 2 different creatures, depending on where you touched it. That alone would have been a major discovery. But there was something even stranger hiding in the numbers. Voyager 1 crossed the boundary at a distance of 121.6 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun. So we are talking about more than 121 times that distance. A truly staggering number, Voyager 2 crossed it at 119 astronomical units. Almost the exact same distance, and that should not have been possible, because the sun does not sit still. The sun breathes. It has cycles of activity. In some years, it is loud, throwing out enormous storms of charged particles. In other years, it is quiet. The difference should push the boundary of its wind outward when the sun is loud and let it pull inward when the sun is calm. Voyager 1 crossed near loud time. Voyager 2 crossed near a quiet time. And yet, the boundary was in almost exactly the same place. One of the senior scientists on the mission, Stamachios Kremigis at Johns Hopkins Applied Physics Laboratory, put it in the plainest possible words. We don't understand why. That is not a small sentence. That is a scientist with decades on this mission openly admitting something fundamental is wrong with our math. Something about the shape of our solar system, something we thought we understood, is not working the way the science says it should. And it took 2 spacecraft in 2 different places to reveal it. Now pause for a second. I want to say something real. If this story is pulling you in, if you are feeling that quiet chill on the back of your neck that space stories sometimes give you, do me a favor. Drop a single word in the comments. Just say Voyager. That is it. 1 word. It tells me you're really here, really listening, and it helps this video reach the people who need to see it. And when you do, ask yourself something. How is it possible that a machine, older than the smartphone in your pocket, is still teaching us things about our own home and the universe that no telescope on Earth can see? Now let me keep going, because we are just getting started. The second big surprise was about temperature. The wind that our sun blows into space is, in the way plasma physics defines it, extremely hot. Not hot like touching a stove. Hot in the sense that the tiny charged particles inside it are moving at incredible speeds. Scientists expected that as this hot wind ran into the cooler, thicker plasma of interstellar space, there would be a slow blend, a gradual cooling as one gave way to the other. Voyager 2 saw the opposite. The drop in temperature at the crossing was fast, sharp, almost a slap. On one side, plasma at tens of millions of degrees. On the other side, plasma at about 30,000 to 50,000 degrees Kelvin. Still hot by human standards, still hotter than anything on Earth, but cool compared to what was pressing against it from the inside. And here is why that matters so much. For decades, scientists had been guessing the temperature of interstellar plasma, estimating it, modeling it, doing their best without ever being able to touch it. When Voyager 2 finally measured it directly, the answer was off from the guess by about a factor of 2. That is not a rounding error. That is a real correction to the picture. And it was only possible because that one small instrument, the plasma sensor, was still alive. It survived on Voyager 2 after more than 4 decades of drifting through the outer solar system. There was also the question of density. Space between stars, it turns out, is not empty. Both Voyager spacecraft confirmed this, but Voyager 2 gave us the sharpest picture. The plasma just outside our solar system is more than 40 times denser than the plasma inside it. Think about that. When you leave the influence of the sun, the environment gets colder, denser, and stranger. Our solar system is like a hot, thin bubble floating in a cool, thick ocean, and we live inside the bubble. And then, the third and possibly most beautiful surprise. The boundary is not solid, it leaks. Not in some poetic, symbolic sense. Actually, physically leaks. Particles cross it in both directions. Some interstellar particles push inward and slip into our solar system. Some particles from our sun's wind sneak outward past the edge and drift into the galaxy. Voyager 1 saw the inward leak first, tendrils of the outside pushing in. Voyager 2, approaching from the south, saw the outward leak. It saw a trickle of solar particles bleeding into interstellar space before it had even crossed the line. 2 spacecraft, 2 directions, 2 different leaks, but the same conclusion. Ed Stone, who had been the project scientist for Voyager since before launch, chose his words very carefully. He said the Voyager probes are showing us how our sun interacts with the material that fills most of the space between stars. Read that again. Interacts. Not ends, not stops, interacts. This was a huge philosophical shift, hiding inside a scientific one. Our solar system is not a sealed room. It is a house with open windows, quietly trading air with the neighborhood outside. Wind moves in both directions at the border. And even at 13 and 16 billion miles from home, both Voyager probes are still in a slightly disturbed zone. A place where our sun's influence has not fully faded. They are, in a way, still standing on our porch, not yet fully in the wild. Now, step back with me for one moment, because the science is only half of this story. The other half is human. The other half is choice. Think about what Voyager 2 actually represents. In the 1970s, engineers using computers weaker than a modern pocket calculator designed a 2 spacecraft mission. They knew that one spacecraft can only tell you what one place looks like. 2 spacecraft could begin to build a real picture of the whole. That was foresight. That was long-term thinking on a scale we barely allow ourselves anymore. But even they could not have imagined what would actually happen. They could not have known that the instrument that would matter most would die on one spacecraft and survive on the other. They could not have known that Voyager 2's plasma sensor would keep working through 40-plus years of radiation, cold, and time. And they could not have known that the choice to send Voyager 2 the long way would place it exactly where it needed to be to fill a gap in human knowledge. It was planned. And it was also lucky. And it also worked. That combination, plan, luck, and follow-through, is what science at its very best looks like. Now it is 2026, and Voyager 2 is at the center of the mission in a way it has not been in a very long time. This spacecraft has 3 working instruments: the plasma science instrument, the magnetometer, and the plasma wave subsystem. Together, these 3 tools are doing something no other machine has ever done. They are giving us a continuous live feed of what interstellar space actually feels like, from a place we cannot otherwise reach. But there is a problem, and the problem is power. Both Voyager spacecraft are powered by the slow, quiet decay of plutonium-238. That decay is like a candle. It gives light, but the candle keeps burning down. Every year, both spacecraft lose about 4 watts of available power. When they launched, each Voyager had roughly 470 watts. Today, Voyager 2 has slightly more power left than Voyager 1. Voyager 1 is down to 2 instruments after losing one in April of 2026. The margin is thin. And every year, that margin gets thinner. So the engineers at NASA's Jet Propulsion Laboratory decided to try something they had never tried before. They call it the Big Bang. This is where the story becomes almost unbearable to think about. Imagine trying to rewire an entire spacecraft. Not one system at a time, all at once. Now imagine doing it from Earth, when every command you send takes more than 16 hours to arrive, and every answer takes more than 16 hours to come back. And you have exactly 1 attempt. There is no test run. There is no dress rehearsal. There is no second chance. If the reconfiguration causes even a small unexpected power spike, the spacecraft's automatic safety systems will start shutting things down on their own. If it fails badly enough, you could lose instruments forever, maybe even the whole spacecraft. The reason it has to be done all at once is because of those safety systems. Every step in between the old configuration and the new one is dangerous. So the engineers decided to jump the gap in one motion, like leaping across a chasm. That is the Big Bang. If it works, Voyager 2 could gain another year of science, maybe more, and if it works there, they will try it on Voyager 1. there is a tiny, fragile hope that even the instrument that shut down in April might be brought back to life. Voyager 2 goes first because it is safer to try. Take a breath here. I want you to notice what is actually happening in the world right now. A small team of engineers is sending commands across 13 billion miles, waiting more than a full day for each conversation to complete, trying to keep alive two machines older than most of the people working on them. That is love. If you are moved by that, share this video with one person, a friend, a parent, a kid who loves the stars. Because stories like this survive when we pass them on. Now let me keep going, because there is more at stake. Keeping Voyager 2's instruments alive is about answering questions no other machine can answer. Questions like this. Why is the edge of our solar system at almost the same distance from the sun, no matter what the sun is doing? Nobody knows. The model said it should have moved. It did not. Something is holding that boundary in place, and we do not yet know what. Why is the boundary leaky? Is that leaking constant, or does it change as our solar system drifts through the galaxy? What shape is our solar system really? Some models draw it like a comet, others like a lemon, others like a sphere. Voyager 1 and 2 are sampling two different points on that unknown shape. Every extra day they operate, we get closer to knowing the true outline of the place we call home. And what is the magnetic field like out there? Voyager 2's magnetometer is still mapping the magnetic field of the southern side of our solar bubble, a side Voyager 1 will never see. And underneath all of this is a truth that most people don't like to think about. When these two spacecraft finally go quiet, there's nothing to replace them, not for decades. There's no other spacecraft anywhere close to that boundary. There is no follow-on mission funded. No rocket is ready to send another. When Voyager 1 and 2 go silent, the map they are drawing simply stops. Every question they raised will sit there, waiting, sometimes for a lifetime. That is why every extra year matters. That is why the Big Bang matters. That is why Voyager 2 matters. Let me remind you what it has already given us. Voyager 2 is the only spacecraft that has ever visited Uranus. When it flew past, in January of 1986, it discovered 10 moons no one had ever seen. It found 2 new rings. It measured the wild sideways tilt of the planet. And it saw a magnetic field so bizarre that scientists are still arguing today. Voyager 2 is the only spacecraft ever to visit Neptune. In August of 1989, it swept past that deep blue world in the last flyby of the program. It discovered 6 more moons and measured supersonic winds racing at more than 1,500 miles per hour, the fastest winds ever measured in the solar system. Then it turned its cameras on Triton and saw nitrogen geysers. Actual geysers shooting frozen material 5 miles into the sky. Triton was an outsider. At Jupiter, Voyager 2 found a new moon in 1979. It confirmed the active volcanoes on Io, watching one of them shooting a plume 125 miles high. It photographed the icy, cracked surface of Europa. Those images were the first serious clues that a global ocean might be hiding beneath the ice. That idea is exactly why we now have Europa Clipper. Voyager 2 planted the seed. Everything since has grown from it. And it was built in 1977. Built with technology from a world before the internet. Designed to last just 4 years. It has now lasted more than 12 times that long. Right now, engineers at JPL are running the Big Bang procedure. Every command takes 16 hours to reach it. Every reply takes 16 hours to come back. Many of the original engineers have long since retired. The new ones had to learn ancient programming languages just to speak to a machine designed before they were born. That is living knowledge, passed hand to hand. When NASA sends a command tonight, they are keeping a living memory alive with patient love. And that brings us back to the biggest lesson. Our solar system is not a fortress. It is a home with open windows. Air moves in both directions. Our sun and the galaxy are in constant, quiet conversation. That is what the textbooks are being rewritten to say now because of Voyager 2. We now know that we are not sealed off at all. We are part of the galaxy, touching it constantly. There is something in that fact that feels almost spiritual. The space between us and the stars is not empty. Our sun and the galaxy are always brushing against each other across an invisible shoreline. We know this only because 2 small machines are still out there in the dark, still whispering back to Earth. You are the reason these stories get told. If you have not already, please consider hitting the subscribe button because when the results of the Big Bang come back, you deserve to hear it first. The signal from Voyager 2 takes more than 16 hours to reach us. It arrives thin, weak, carrying data from a place no camera can see, and still, it comes. Voyager 2 is the twin that told us what the space between the stars is actually made of, not by theory, but by direct touch. And now it stands at a milestone. There is no backup plan. There is only this one chance to buy Voyager 2 more life. If you want to know what happens, stay with this channel. We tell the real story at the pace and the weight it deserves. The story of Voyager 2 is a story about a small team on a blue planet speaking to the stars. When you look up tonight, remember that past the line where our sun's voice finally fades, A small machine is still listening, still measuring, still sending its faint signal home. And as long as that signal keeps coming, we are not alone in the dark. We reached out, and something we built is still reaching back,